So that actually sets me up nicely because between getting from the front row there to over here, I probably switched associations with 3 or 4 networks, right? And just to maintain a single identity was a big issue. So MobilityFirst architecture is trying to address a future internet wherein the number of mobile devices is going to be significantly larger than the number of fixed devices. So this is actually a multi-university effort. Rutgers is leading in this, and there are 7 other universities participating in this. So, so the motivation is clear. In the future, there'll be more mobile devices. And some of the scenarios or the problems with mobile devices is disconnection and variable link quality at the edge. And we believe that this has implications for how things are done at the core as well, right? So, and it's not only mobile devices, but also sensor networks, Internet of Things, and vehicular traffic are some of the things which will be increasing in huge numbers. So the architecture proposed by MobilityFirst, the key features include name and address separation so to support mobility, keep identity across different network associations, public key as the global unique identifier that will be used as the name for hosts at least, and also possibly for other things such as content, context, and services. Storage aware routing, wherein we actually exploit the resources available within the core and at the access networks, such as storage, to be able to support mobility scenarios such as disconnection and variable link quality. So there are a few other things that are proposed in the architecture. I won't have time to get into all of that. But I'll get into 2 main things in this talk, setting up the actual demo, that is the name to address separation and addressing of packets using the global unique identifier, and the storage aware routing aspect of MobilityFirst. So we believe that there are a few very distinct things from the current setup of the internet, which is TCP/IP mostly. And we'll be exploring some of those ideas. And it is a clean slate approach to the design, but we'll take it to whatever point and see if there are things that can be applied incrementally as well. So the first basic concept that MobilityFirst uses is the name to address separation. So the name here we are referring to as a globally unique identifier that every mobile host or content or context or services can use. And in the case of host, this can be a public key that can be used to identify the host. So these mappings between the globally unique identifier and the network address we propose to store in a globally distributed name resolution service, which can be accessed quickly from the edge, right? So, and latency becomes a concern here when nodes are constantly moving between networks, and other nodes need to reach these mobile nodes. So, as an example here in the figure, if a mobile device first attaches to network 1 and then moves, is mobile, the user travels from one place to another, associates with another network, it still keeps its same global unique identifier, and the mapping is changed in the name resolution service, which can be retrieved by any other entity connected to the network. So just as a note, we've done some early evaluations using simulations at internet scale using data from DIMES database, which essentially the number of nodes within considered within this architecture is similar to that in the present internet. So the proposal here is a DHT between the routers within the network, and the routing between these DHT endpoints closely coupled with the routing that happens within the network itself. So the reachability information at the routing layer is used to map or distribute the GUID to NA mappings of these mobile nodes. So the evaluation shows us that at the internet scale, we can still achieve latencies close to or within 100 milliseconds, which can help us support mobility and even real-time applications running on these mobile nodes. So real evaluations are currently ongoing on both on GENI as well as Planet Lab. So the second aspect that I'll be concentrating on here for the demo itself is storage-aware routing, wherein we're trying to exploit the storage within access as well as core network to handle endpoint disconnection and variable link quality, right? So the idea being, if a mobile device moves from one network to another network during its mobility, during the transition, it can be disconnected, but also it can be having a variable link quality during the time, at which point the access or the edge node can choose to store it rather than having to go over a bad link quality, right, and waste the shared spectrum. So using these two things, which is GUID-based addressing and storage-aware routing, we can show how we can address a scenario such as dual homing or even partial disconnection of a mobile device connected to two different networks. So if we think a multi-home device connected to 4G or 4G and Wi-Fi or 4G and cellular, Wi-Fi and cellular, then the routing, the storage-aware routing that we deploy within these networks and any other interdomain routing protocol can make use of this information, which is one is that it's connected to two different networks, and this association is actually reported within the name resolution service, as well as the link quality, the path quality information, which is exported not only to the last hop or the first access point, but also deep into the network itself. So if there are two divergent paths to the endpoint on this multi-homed endpoint, then the decision as to which path can be used for the delivery can be done at an upstream router, a bifurcation router, and actually achieve better delivery efficiency in this case. So we've defined, so along with the protocol design, we are also starting on a prototyping of the architecture itself. And the key components here are a router, a MobilityFirst router, and as well as the client stack that we have currently have running on Android as well as Linux platforms. So the protocol stack involves a MobilityFirst network API. So build individual components first, and then define the entire protocol stack, which we want to deploy on GENI nationwide, as many campuses as possible, and have some live running, as in long running evaluation of the overall architecture. So our router is a click-based router, and at this point we've implemented the storage-aware routing protocol, as well as the name resolution service. So the close coupling that I mentioned before between the name resolution and the routing, can be made possible by running the name resolution service either co-located or on the router itself, and this can be on a subset of the routers. So the close association allows for dynamic rebinding of the GUID to network addresses, especially when you have a mobile client. So all of the things that I've talked about is related to hosts, but also things get more interesting when we talk about context, dynamic context, and content that can be replicated or cached throughout the network. So we've also implemented a client protocol stack and MobilityFirst network API, which allows clients to send and receive messages over the MobilityFirst network. So so there is no IP used within the protocol, and it's complete layer 2 messaging. And In order to do that, we use the GENI Mesoscale deployment. For the purposes of our prototype evaluation, we're thinking of multiple of these core edge networks which have 4G and Wi-Fi capability connected eventually to each other through a core backbone. So the phase 3, as I said, we want to do a larger scale deployment. And there is a varied type of resources available on the GENI backbone. Some of this can be the real hardware such as ShadowNet and so on, or OpenFlow switches. Currently, we are just going for the host-based click router implementation, but we would want to add in these real hardware components as well, so that we can do higher performance evaluations. So this is the goal for us, at least with respect to GENI, is to try and have multiple campuses connected up to the backbone and see if there are interesting evaluations for mobility across these campuses, whether it's emulated, however it is achieved. I mean, most likely we'll have to emulate, but is that really useful is one of the questions we would like to answer. So today's experiment, it's sort of an ongoing thing, and we've just gotten started using GENI Mesoscale deployment. It uses 2 edge networks, both of which have Wi-Fi and WiMAX networks, connected up to the GENI backbone, the Mesoscale deployment, where we have about 7 routers running, the MobilityFirst click-based routers, along with the name resolution services running on each of the routers, right? So, and these 2 sites are the BBN and Rutgers sites. So I believe that this is probably the first, where we are trying to bring in the edge networks into the backbone. So the application is quite limited at this point. We're still looking at sort of content delivery applications end-to-end, wherein you have mobile clients or servers at these endpoints, right? So this is the proposed network graph that we shared with the BBN folks, and we said we would like to deploy about 7 routers which have which are connected within the core, and there's some path diversity within the core, but also has the potential of end-to-end independent paths. And this gets interesting because we can have Wi-Fi and WiMAX independently connected up to the backbone, and then routing decisions within the core can be made to split traffic across these 2 different paths. So here, when I show these routers, it's still sort of a single domain evaluation, and that's consistent with our current implementation of a storage-aware routing protocol, which we think of as an intra-domain routing protocol. But the next step is to look at inter-domain routing protocols as well, and we can see each of these routers to be independent networks, in which case the end clients are multi-home to these different networks. And once we have the implementations for the inter-domain routing protocol, those can be evaluated in a similar context. Right, so we proposed that topology and then went to the BBN folks, and BBN came back to us within a week or so and said, why don't you guys, so we can have this independence of these 2 separate paths by having VLANs on NLR and I2 backbones, and use these hosts. So these are actually the switches connecting up the NLR and the I2. So the I2 is mostly a south backbone, and the NLR is mostly the north. And they are connected up at Atlanta, wherein so we can have an end-to-end path between NLR endpoint and a I2 endpoint. So at these points of presence on the backbone, there are these GENI hosts, and essentially, the BBN helped us choose, which nodes we can use for mapping our virtual topology onto this physical network. Right. So, and this is an interesting animation. I have to give credit to my colleague Ivan put this together, which shows, essentially how the physical topology can then be mapped to the virtual topology that we are interested in. So one interesting thing is that the latencies between these nodes is quite varied. Some varies between 1 millisecond up to 180 milliseconds end to end. So when we choose these nodes and how we map it to the virtual topology that we are interested in exploring, I think we can do interesting things like the low latency nodes can be put together and in an intra-domain evaluation, and the high latency nodes can be put together as part of different networks on an inter-domain evaluation. So the final, getting into the actual demo, right? So this was a topology, and what we did in between the connection point. So both Clemson and Georgia Tech are connected up to both of the VLANs. And so we actually ran a bridge there, which would bridge the traffic at the core. So, all of these things, doing things at layer 2, as well as bridging VLANs, needed just a little bit more effort. But we got a lot of help from BBN, and so we're still putting out fires. But but we were able to, get an end-to-end application running. So part of the evaluation here, or the interesting things that we want to look at, is the storage-aware routing protocol that we did. We were thinking more as a intra-domain routing protocol. How does it behave when we start to look at inter-domain latencies between the nodes, right? And some of this actually became evident to us, during the evaluation, during the experimentation. So the application here is there are 2 clients, one at BBN and one at Rutgers. Both of them can be hooked up to WiMAX and Wi-Fi. So what we've done is one of them as a content publisher and another one as a content subscriber. So I'm going to quickly start up the, so I'm going to start up the content subscriber, which also has a GUID. Like I said, every host or application can have a GUID. So as soon as the content subscriber comes up, it publishes it. So we have an association protocol. It publishes its information out to the network. And what happens is the mapping is posted into the GNRS, or the Global Name Resolution Service, that we're running on the routers itself. So it's still a bare bones map. So I think the resolution is a little bad, after the switching to the monitor to the screen. But essentially, it has each mapping has 3 entries here. One is the GUID itself of the host. And in the case of the subscriber, this was 201. The second one is the network address or locator. And in the case of the subscriber 201, here it shows as NA9, NA:9, right? So NA, the first part of the GUID to name address mapping, is the network name. We use a flat network address name. And this is more relevant for the inter-domain routing protocol. So in the case of the intra-domain routing protocol, the second part of the mapping is more relevant, which is a local routing identifier. And in this case, the subscriber gets a local routing identifier, which identifies where it can be reached within the domain. Similarly, I've already brought up the content publishers protocol stack, and it also has a GUID, and that's 101, and that's running at BBN. I'm going to start up the file sending application, which then pushes out these, what we call the chunks, which are large data segments, onto the protocol stack, which then fragments it and sends it over layer 2 to the next hop router using the hop by hop protocol. So what's happening right now is on so the other visualization screen here is a work in progress, but it's something that both WINLAB and NICTA have worked on to have a visualization for OMF-based experiments. So what we're seeing is the data that's been collected from the actual experiment running right now on ProtoGENI, which have been OMF and OML enabled, which allows us to push all of the data collected within the routers out into a central repository off of which the visualization is running. So let me quickly bring up the topology slide. And the mapping here is 1-to-1. So on the right-hand side is the content subscriber, and on the left-hand side is the content publisher. So the content publisher right now connects from a WiMAX network at BBN, and the first hop router. So I'm not sure if we lost the core. Okay, so this is. Okay, so that was just a visualization thing. So, we've been under constant pressure of losing the core in the last couple of weeks, but managed to hold on. So the first hop router connected to the Wi-Fi connected publisher then pushes it hop by hop onto the other routers within the path. So on the Rutgers side, the content subscriber is connected to both Wi-Fi and WiMAX networks and connected onto the MobilityFirst network deployed on the ProtoGENI. So there are two possible path options here, but the last hop WiMAX the latency is much higher than that of the Wi-Fi, which is about up to 50 or 60 milliseconds larger. So the storage-aware routing protocol makes a determination that the Wi-Fi path is the more efficient one and pushes most of the data along that path. So I want to quickly show. So we are starting to receive the content actually from the Wi-Fi path. So one thing I wanted to show is that it supports disconnection both at the sender side and the receiver. So the sender can disconnect after pushing all of the content out, and the content would be delivered based on this GUID of the destination by the routers, which can make use of intermediate storage. So what you saw on the bottom screen is essentially the client receiving the chunks on the Wi-Fi path. So I can kill the client on the Rutgers side. Wrapped up? Okay. So I guess if people are interested, we can sort of continue on the demonstration. But yeah, I mean, the storage-aware routing protocol handles disconnection and determines which path might be more appropriate by estimating the link and path qualities. So that was our demonstration, and so we want to keep this as an ongoing experiment on GENI, and hopefully have more campuses connected up, and that will be, within the MobilityFirst group itself, there are multiple campuses which we are planning to put up into the core, but other campuses participating as part of this experiment would be useful as well.